Hi everyone, today we're going to be going over climate, but not necessarily today's climate or current climate change, but climate categories, the controlling factors of climate, and paleoclimate proxies. But first, I just want to define climate and make sure we all understand that climate and weather are very different. Weather is a state of the atmosphere at a specific place and time as regards to heat, dryness, sunshine, wind, rain, etc. However, climate refers to weather conditions such as temperature and precipitation patterns, seasonal fluctuations like rainy versus dry seasons that prevail in an area over a long period of time, so decades or longer. And so this is why we refer to long-term patterns as climate. So to get started, let's talk about some climate categories on Earth. The 5 main categories that Vladimir Koppen defined in the early 20th century include tropical rainy, shown on this map as orange, and defined as equatorial regions with year-round average temperatures above 18 degrees Celsius or 64 degrees Fahrenheit. No true winter, may have a monsoon season, and includes both tropical rainforests and savannas. The second category is dry, shown in this map as yellow. Dry climate regions include deserts and grassy plains, regions that receive little precipitation, and evaporation and transpiration rates exceed that of precipitation rates in most years. The third climate category is mid-latitude, humid and warm, or on this map, temperate in green. This category includes regions with warm to hot summers, mild winters, and coastal climates like the Pacific Northwest and the drier Mediterranean. The fourth climate category is mid to high latitude, humid and cold, or on this map is called continental in the turquoise color. This category includes regions with warm to cool summers, cold winters, and areas with deciduous to coniferous forests, such as Canada and the northern US. The fifth and last climate category is polar climates, shown in this map as blue, and this includes tundras and ice caps with no real summers, and also regions at very high elevations, such as mountainous regions above the tree line. So now let's move on to the factors that control climate. These include, but are not limited to, solar radiation, latitude of continents, global wind patterns, global ocean currents, mountain belts, surface reflectivity, or albedo, atmospheric composition, and astronomical factors. Before we get into each one of these controlling factors, first we have to discuss positive and negative feedback. Climate feedback occurs because all of these factors that control climate are so interrelated that each one can affect the others. The way in which it affects the others is called feedback and can be positive or negative. An example of positive climate feedback is when Earth's temperature cools, glaciers and ice sheets become more extensive and therefore reflect even more sunlight, and then Earth cools more. This creates an exacerbated cooling effect, meaning the cooling is emphasized by this feedback mechanism. However, there can also be negative or balancing effects, such as when temperatures rise on Earth, that causes more evaporation, which causes more clouds, which causes cooling temperatures because of cloud reflectivity. These can go the other way around. For example, with the glaciers, if you were warming Earth and ice sheets are melting, you're going to have an exacerbated warming effect because the ice sheets reflect sunlight, and when they go away, there's more land or water to absorb sunlight, and therefore Earth will warm more. So all of these feedback loops can go in either direction, and they're common in pretty much all the factors that we're going to discuss that control climate. Starting with solar radiation plays a crucial role in Earth's climate, and this is pretty obvious, but one thing you might not know is that the sun has not been at the same intensity throughout Earth's history. For example, during the Precambrian, the sun's energy was almost 30% less than it is today, meaning that Earth would have been really, really cold compared to today. However, atmospheric composition, which we're going to talk about later, played a role to balance out Earth's temperature. Because CO2 concentrations were much higher in the Precambrian atmosphere, this helped keep Earth warm enough to support life during the sun's less intense period. Additionally, surface reflectivity is another climate controlling factor that depends on solar radiation. Solar radiation is not absorbed by every surface on Earth. It depends on the composition and color of the surface. For example, light surfaces such as ice or snow reflect collect a lot of solar radiation or sunlight and therefore act as a cooling mechanism for Earth, whereas dark surfaces such as continents and specific surfaces on those continents such as asphalt roads can absorb a lot of that solar energy, therefore warming the Earth. The percentage of solar radiation that is reflected from a surface is what we call that surface's albedo. In the upper right corner here, I put 4 main types of surfaces that we know on Earth and what their albedo is. Water reflects about 10% of the solar radiation it receives. Continents reflect only about 4%, whereas ice and snow reflect up to 95% of solar radiation they receive, and clouds reflect up to 90%. And then the average albedo of Earth today is around 30%. However, as ice caps and glaciers melt, quickly goes down, therefore warming the Earth. And this has changed and fluctuated a lot throughout Earth's history. Latitude of continents. The latitude of continents plays a role on how much Earth absorbs solar radiation because solar radiation hits the Earth at the equator more directly and therefore is more intense and causes more heat, whereas it hits high latitude regions more indirectly or angled and therefore is much less intense and is therefore cooler in those regions. Throughout Earth's history, the precision and fragmentation of continents has affected the amount of solar radiation absorbed or reflected, which affects climate. It also affects ocean and air circulation, which are 2 other factors we're going to get to in a minute. Starting with air circulation or global wind patterns, we know that warm air rises and cold air sinks. This is why in this picture to the right, we see that warm air from the equatorial regions rises and therefore travels to the poles where it then sinks and it travels back to the equator and then rises again. And this is not only controlled by temperature but also pressure. Air moves from high pressure to low pressure areas. However, because of Earth's rotation, this is not a straight line that the air travels from the equator to the poles. And this effect of Earth's rotation on the travel path of wind patterns is called the Coriolis effect. The Coriolis effect works something like shown in this picture, where Earth's rotation affects the path of anything going straight toward the pole from the equator. The path is deflected because Earth is rotating. So if we take the Coriolis effect into account, we see that global wind patterns look more like this. There are low and high pressure regions, there are low and high temperature regions, and these cause a bunch of small cells, and there's also the rotation of the Earth. All of these factors control wind patterns together and therefore cause a bunch of angled wind cells that circulate air throughout the Earth. Temperature, pressure, air circulation, and the Coriolis effect, however, do not only affect wind patterns, but they also affect ocean circulation. The circulation of the ocean is controlled by surface currents and deep sea currents. Surface currents are mostly controlled by wind, and therefore they'll tend to follow a pattern similar to what we saw on the previous slide. However, deep sea currents, which affect the surface currents and ocean circulation as a whole, are controlled by density, which is controlled by temperature and salinity of the water. Overall, it creates a pattern similar to what we see in this map. And because ocean currents transport heat, they subsequently affect air temperature and climate. The next controlling factor of climate we're going to talk about are mountain belts. Mountain belts can disrupt global wind patterns and precipitation patterns. As air rises along the windward slope of the belt, it cools, moisture condenses, and precipitation occurs. This is sometimes termed rain out. All the rain occurs on the windward side of the slope. Then on the lee side of the slope, the air warms and precipitation does not occur. This causes the dry rain shadow regions on the leeward sides of mountain belts. Another really important controlling factor of climate is atmospheric composition. We hinted at this a little bit when we talked about solar radiation and the Precambrian CO2 concentrations helping to warm the climate because the sun was less intense. This is because CO2 is a greenhouse gas along with methane, water vapor, and many others that we just don't have time to talk about. These greenhouse gases absorb radiation, and therefore an increase in these gases causes warming in the atmosphere. Early Earth had a much higher percentage of CO2, like we discussed earlier, and almost no oxygen, which likely had a strong influence on how life evolved. And life also had an effect on atmospheric composition. For example, when photosynthesizing organisms evolved, oxygen began building up in the atmosphere, and CO2 became much more depleted because these photosynthesizers took up CO2 to create oxygen. So what do these fluctuations in CO2 concentration cause? Well, for example, an increase of CO2 in the atmosphere can cause an increase of photosynthesis and therefore a subsequent increase in vegetation, which causes an increase in transpiration and therefore an increase in precipitation. That is a way that CO2 can directly affect climate other than just warming. However, if you think about this as actually a negative feedback, the feedback loop comes in when an increase in CO2 causes an increase in photosynthesis. The increase in photosynthesis will cause a decrease in CO2. Therefore, this is a balancing act, balancing the levels of CO2 in the atmosphere. Another factor that can influence the CO2 concentrations in the atmosphere is chemical weathering. Chemical weathering can decrease CO2 concentrations of the atmosphere, and tectonics, such as mountain building events, increase the rates of weathering and therefore can decrease CO2 concentrations in the atmosphere. We also mentioned methane as a greenhouse gas. Methane is actually 20 times more potent as a greenhouse gas than CO2. Methane is released into the atmosphere by things like cows, termites, and the decay and decomposition of organic material. However, most prominently, the melting of frozen methane hydrates could increase methane in the atmosphere most drastically. This is because at certain water depths, temperatures are cold enough to freeze methane gas into frozen methane hydrates, which then can collect on the ocean floor. These methane hydrates can also collect in permafrost. It is currently estimated that on Earth today, these methane hydrates contain twice as much carbon as all fossil fuels combined. So if they melted, that would release an enormous amount of methane into the atmosphere, causing a lot of warming considering how strong a greenhouse gas methane is. However, even as strong a greenhouse gas as methane is, water vapor is the strongest. However, water vapor is not a large focus of tackling today's climate change because it is largely controlled by non-anthropogenic causes, and therefore we can't really do anything about it. And lastly, in terms of atmospheric composition, we'll go over volcanic activity and forest fires. Volcanoes and forest fires can release volcanic ash and certain aerosols that can block or reflect sunlight, subsequently cooling temperatures. However, volcanoes and fires can also release gases such as CO2 and methane, therefore warming temperatures. So there are very complex pathways of which volcanic activity and forest fires can affect the atmosphere and therefore the climate. The last climate controlling factor we'll discuss is astronomical factors. Earth's orbit changes regularly from elliptical to almost circular. Additionally, Earth's tilt on its axis changes regularly from around 22 to 24.5 degrees, and these changes can heavily affect climate. For example, an elliptical orbit compared to a circular orbit will cause stronger variations in the sun's intensity because Earth is so far away at either end of the elliptical, whereas at either side of the elliptical it is much closer to the sun. Additionally, a larger tilt on Earth's axis can cause larger variations in latitudinal temperature gradients on Earth, whereas a smaller angle of tilt will cause less intense variation along this gradient. Lastly, a pretty obvious astronomical factor that can affect Earth's climate, such as what we saw at the end of the Mesozoic with the KT extinction event, is a meteorite impact. Meteorite impacts can throw up dust and rocks and ash into the atmosphere, causing cooling effects. So now what I want to discuss is how we can reconstruct ancient climates. How do we know how the climate has fluctuated through Earth's history? We can use things such as paleoclimate proxies to reconstruct Earth's past. These include things like the composition of calcareous fossils, such as mollusks and corals. Mollusks and corals make up their shells or skeletons with calcium carbonate, and calcium carbonate has both carbon and oxygen in its chemical formula. We can use oxygen and carbon isotope ratios from these fossils to deduce information about the climate during the time that that organism lived. If you want to know more about how we use oxygen and carbon isotopes to reconstruct paleoclimate, you can check out my oxygen isotope and carbon isotope videos. The next proxy we can use is dendrochronology. Dendrochronology is a method in which we use tree rings to reconstruct past environments and climates. We can do this because trees grow in annual rings, and their thicknesses and composition can tell us a lot about the environment during the time they were growing that ring. For example, wider or thicker rings can tell us that during that growth period, the tree received more rainfall and optimal temperatures, whereas thinner rings can tell us that the tree was receiving minimal rainfall and colder temperatures during that growth period. Similarly, we can use plant fossils such as leaf shapes to understand similar environmental conditions. For example, smooth leaves are common in tropical warm environments, whereas jagged leaves are common in colder climates. We can use pollen grains similarly. Pollen grains are shown here in the bottom right picture, and you can see these have really distinctive morphologies. These morphologies can tell us something about the vegetation living that area during that time, and can therefore tell us something about the paleo environment and paleoclimate. and the study of pollen grains in this way is called palynology. And the last paleoproxy I want to discuss is foraminifera. Foraminifera can not only be used for their composition, for example, oxygen and carbon isotope ratios because they're made of calcium carbonate, but can also be used based on their morphology and coil direction. Basically, foraminifera are microfossils, and some types of these foram species can actually coil differently depending on temperature. If the water temperature is warmer, certain species will coil to the right, whereas if the water temperature is cooler, these species will coil to the left. These proxies are especially useful because we can use them in conjunction with other proxies to get a really good idea of the environment and climate conditions that were occurring during certain periods in Earth's history. The last thing we're going to discuss is current global warming. Global warming, like we discussed earlier, can be caused by greenhouse gases, and today this is what is occurring. Greenhouse gases such as CO2 and methane from burning fossil fuels, clearing forests, and agricultural activities are causing warming on Earth today. Additionally, solar radiation absorption has increased, largely because areas covered in ice and snow are melting. Additionally, melting permafrost and tundra releases even more methane and carbon dioxide, which were trapped in gas hydrates, into the atmosphere, and this is a positive feedback loop that exacerbates the effect of warming. Periods of warming are common throughout Earth's history. However, the rate at which Earth is warming today is unheard of, and this is because of the large impact that humans are having on the climate. Because of this rapid rate of climate change, many organisms are not able to adapt and survive and therefore are going extinct. This is what I talked about in the previous video with the onset of the sixth mass extinction. Some of the organisms that have been hit heavily include plants, which have specific climate needs, and therefore when climate changes rapidly, they cannot survive. Additionally, polar bears have already started to show the effects of climate change only in the last 30 years. The average polar bear weight has become 15% less. Additionally, corals are bleaching and dying, not only because of temperature, but also because of ocean acidification, and this is leading to massive local extinction events because of how many species rely on these corals. Scientists estimate that 150 to 200 plant, insect, bird, and mammal species become extinct every 24 hours. This is nearly 1,000 times higher than the natural background rate, and it is greater than anything the world has experienced since the vanishing of the dinosaurs 65 million years ago. This graph on the left shows the increase in atmospheric CO2 concentrations from 1960 to today, and this is the main factor driving this sixth mass extinction. Unfortunately, we ended on a pretty sad note, so before I let y'all go, just know that it shouldn't be a sad thing that human-caused climate change is a thing. It's actually a really amazing thing that we can even recognize it. We're the only species on Earth that has ever been able to foresee an extinction event and actually know what's causing it, and therefore we can actually do something about it. That is what we should be focused on, and that is not sad at all. That is amazing, and we should definitely take advantage of our insane intelligence as a species. So with that, thank you so much for watching. I hope you learned something about climate categories, the factors that control climate, the ways in which we can reconstruct ancient climates, and a little bit about current climate change. Thanks again for watching, and I can't wait to see you all next time. Bye.